Hello, everybody. So my name is Mansour. I'm with the Esri. I'm a senior architect. I blog about big data and geospatial at Thunderhead Explorer. Don't hesitate to email me at mrad.com, and you can follow me on Twitter if you guys want. I tweet some pretty cool stuff, not like I'm sitting on my back eating a peanut butter jelly sandwich or something like that. So this is what's going to feel like for the next half an hour, what they told me, and actually, this is a tribute to Leonard Nimoy because of space and time, and he was an amazing person, and rest in peace. So let's get going. I don't know if you've seen that book actually at the O'Reilly place here. I think we should really check it out. There's some really amazing stuff in there in that book. Josh did an amazing job, and so is Sean. But actually, one of the things that they have in there is they have a section on geospatial. And they're actually going to be doing some of the taxi data that everybody on this planet here has done already, and kind of appropriate to do it for New York City taxi. But they're using that geometry library that is in this GIS tools for Hadoop that we have. Don't get fooled by the name for Hadoop. We did that a couple of years ago because we want to capitalize on the name of Hadoop. But actually, there's an amazing, it's a open source Apache license GitHub project, and has also a bunch of high UDFs. But the key here, it has a full computational geometry library, and that's what Josh used in his analytics to do that. You can analyze points, lines, and polygons, envelopes, and we have a full computational geometry engine. So if you want to find me what polygon intersects with what point, if a point is inside another polygon, or what line crosses what, these are all available in there, which is pretty cool. We have some spatial operation, buffering, which means take a point, find me everything within a certain, find me within 5 kilometers of it, what it will look like. If you want to take convex hulls, and has spatial indexing, which I tremendously use in a lot of my analysis. If you went to actually Michael's talk on Spark SQL and what's really exciting in the Spatial Hive, they can do UDFs. So at the time, we invested a lot in Hive. At the time, it was the big thing to do. And we invested a lot of time in Spatial Hive. We introduced a bunch of UDFs to be able to do spatial operations. And you can basically now spatial join, in theory, two RDDs together using the ST contains. So now you can take a couple of records to a couple of spatial features and join them together based on not an attribute, but based on their geometry. And that classically, you don't do that. You don't have that kind of capability in there. So in that project that we showed, the GIS tools for Hadoop, we have that. And what is the neat thing about it is, since Spark SQL understands the Hive UDFs, we just use these things right there and there, and guess what? We can do now spatial operation in Spark SQL, which is pretty cool. I want to jump back a little bit to the old days again, kind of funny old days is a couple of years ago, which is thinking in MapReduce, which is kind of interesting. And what you do when you're thinking in MapReduce, you have a K1V1, which is a key valued as an input, and you basically map it, and you end up emitting a list of K2s, V2s. And usually mappers for filter and transformation. And then in the reduce phase, you want to be able, you take the K2s and the list of the V2s that were associated, and you group them together to produce another list, which is pretty cool. And that's kind of how we've been thinking along the ways, and it's pretty neat. But what we want to do is we wanted to be able to do kind of a geo MapReduce, or kind of what we're going to be doing now with GeoSpark MapReduce. And what is that intending here to do geo MapReduce is actually creating something we call a density map. A density map is actually, that is aggregating by space things together. So we've been aggregating a lot by attribute, but what we want to do is we want to aggregate by space, and whatever things fit in the same space together, this is what we collect and we aggregate by. And when you want to color code it, you color code by what we call the population field, the number of items in that cell, and that's how you create a simple density map. Pretty cool, pretty easy, and it's pretty nice. For us in geospatial, every time we have to do something like that, we have to cut our space into these little quads or in this little portion, and by working on that, works out really well. So a classic implementation in MapReduce will become something like that. In Mapper, you take a line number, you take a text, you split it up, because most of the time a lot we see is CSV files. You split it up, you write some math to convert it to a cell value, and you emit the cell by 1. And in the reduce function, you basically, for that particular cell, you aggregate the number of ones that have accumulated on there, and that is what you emit, and that's the population count. Well, this is pretty, but actually this is prettier in Spark Scala, and with a little bit of try-catch block handling to make sure there's no bad input, because I'm not a data scientist. I never create myself to say that. I'm a data janitor, because a lot of the data that I get is junk a lot of the time. I spend 80% of my time cleaning data. I'm not a data scientist. I'm a data janitor, because I need to clean code all the time. And so putting stuff like that and putting try-catch, and actually I should put an accumulator here to make sure things are fine, makes life really well. So here I flat map the data because I emit an option. If it's things, I emit nothing. And this is where I can take the data from HDFS, bunch of them, and turn it into a certain output into HDFS. And we can do some pretty cool things with that environment in here. And so one of the missions that we're working on, since we're on a Star Trek theme here, that we want to go out, is we want to use that same scenario here to find ships that are very closely traveling together. And this is a big problem in a lot of harbors and a lot of, Navy operations and a couple of other three-letter companies in the government that we work for. And so actually there's a very important feed that is put out up there called the AIS. Every ship in the world that travels actually emits that AIS feed. They tell you what's the date of the emission, where's the date and time, the lat long, how it is heading, what's its status, what's its voyage, what's its identification, they call it the MMSI, and what's the draft of the information. If you want to, your tax dollar are paying for a sample data you can download from that URL, by the way. It's a good way to experiment with some of these ideas in here. So in this particular case, we dumped it into Accumulo, okay? And because we wanted to create a cell-level security on who can access that particular type of information. And so we massively ingest through streaming this AIS data on a continuous basis. The places where we worked on, we got the data as an FTP site. Can you believe it? We still use FTP, which is pretty cool. They dumped the data in FTP site, and we basically streamed that information into Accumulo. Accumulo, as you know, is a key value pair storage with cell-level security. What we've done is we geospatially enabled Accumulo to be able to quickly locate, using the geometry library, some spatial information very much on time. Of course, Accumulo dumps its data in HDFS. That's how it produces resiliency. Now, when it comes down to finding ships that are closely traveling together, we end up using Spark for that one. And so we run these Spark jobs that does these proximity searches, kind of very much like the density analysis that I showed you, where it dumps back the data into Accumulo in such a way that we can expose it back out. And we fronted the whole thing with Tomcat to be able to visualize the data in our visualization tool in here. Now, because I'm one of the cool kids in town, Docker is the latest thing that everybody's really loving life about. So we created a compartmentalized version of this whole thing, containers for the Hadoop, for the Spark, for the Tomcat, for the Accumulos together. And we were able to deploy that using Docker very well, very nicely, and be able to spin off these things up and down very, very, very neatly. So what it ended up coming back is we end up visualizing all this data on a map. And we can see, using the highlighted cyan colors, which ships are co-traveling together outside the harbor. And they're very close to each other because they're dangerously close to each other in here. And that was pretty neat implication, pretty interesting application that we built for a harbor that we were working with in here. You've been seeing a lot of Hadoop, but actually that's not true, actually. If you've been listening to the keynote, a lot of stuff like that, in my professional service experience here right now, I'm not seeing actually a lot of Hadoop. Or actually the Hadoop that I'm seeing is not in the form that we have been typically seeing. And I'm entering what I call now the no Hadoop SQL zone in a lot of the things that we're doing right now. And one of the things that we wanted to do is, for example, do aggregation of data on the fly. If you notice, the type of jobs that I've been doing, by the way, have always been what I call batch jobs. That means I run my analytics and I produce this massive amount of data and then I turn around and I visualize. Well, you know what I want to do right now is I want to take this big data and on the fly compute that, for example, that density analysis and stuff like that. And of course, everybody's been talking about the New York City taxi data, and you can get it through the Freedom of Information Act that Chris Wong put out there. And it has the pickup location, drop-off location, number of passengers, and all these interesting criteria. Why we like this data so much is because it has space and time in it, and space has a bunch of things like pickup location, drop-off location, and pick-up time, drop-off time, which is pretty neat. Now, we collaborated with our friends at MemSQL here, and please go check them out. They're very cool folks. A lot of databases out there they say that they put geospatial in their database, but actually kind of they're faking it. Why? Because they put the latitude and longitude as just a double field in the database. And when it comes down to spatial query, well, they're doing a where clause on the latitude, longitude, where, a range query. Well, that does not work very well, especially if you have complex things like polygons and lines and stuff like that. So what the folks at MemSQL did here is in-memory databases, they geospatially enabled the types. So now the pickup location and the drop-off location is not, notice, a lat long location, but actually it is a point. So they introduced point as a type, just like a string, doubles, integer, and all that stuff like that. And on that, you can perform now dynamically on the fly data aggregation. So you can do a select, star, group by, and all that stuff. And so what we did, we at Esri, because our platform is extensible, we were able to, through this thing we call the SOI, the Server Object Interceptor, we do not support this thing natively out of the box because, well, they just came out with it. So quickly, actually, we spent last week, the MemSQL and us, stood up an Amazon instance for me, started up their instance, loaded the 170 million data records onto the Amazon instance up there. And for me, what it turned out to be is to go out and using my out-of-the-box experience to go out and query this data. And that's exactly what I want to show you here. I started up my little server, and hopefully not iTunes. Sorry. Yeah, I don't need iTunes. Okay, I started up my server. And what I have is, this is the standard out-of-the-box equation. And through what we call the extension mechanism we have, I can wedge in a data source. And now I'm talking to MemSQL in here. And I'm going to go out and visualize that 170 million record aggregated. Now, to show that things are working for this demo, to make sure I had this debug line that everything, to show a red line that actually I'm querying the data, which is pretty cool. I have an option of changing the base map because I don't like that base map in here. And I want to go to New York City in here. So I am dynamically querying the data in here. Okay? And I'm going to now go in and zoom in directly to Manhattan. And when I zoom into Manhattan, this thing went out and queried the 170 million record on the fly and dynamically generated a heat visualization of the data. Now that is pretty impressive. The fact that I can do this, and if I keep on zooming in, it's actually keep on doing that. And when I'm panning and zooming and stuff like that, and I made that border on purpose, it's going out explicitly querying this data, aggregating it, and I'm bringing it back and turning into little cells and visualizing it on the map. Pretty cool, pretty impressive, seriously. That was very good collaboration between the MemSQL and us, and to be able to do that kind of aggregation on the fly is pretty slick, okay? So that is one fusion of things that we do together. Now, another application that we had to do was something we call dynamic segmentation. And a Vulkan mind meld, no pun intended, of what dynamic segmentation means is the following. Every line, like for example, we do that for the United States highways. Every highway has a particular milepost, if you notice, when you drive by it. The United States Department of Transportation actually defines a set of attributes that are associated with different mileposts. For example, the number of lanes, the type of asphalt, and usually there's about 90 properties, believe it or not, that your tax dollar are paying for that associate with every one of those things. And what you have to do right now is you have to take that information and segment it into what attribute is associated with what. Okay? Typically this, when it runs, and they run it for a year, takes hours to run to do that process in here. Okay? And so what I needed to do is I wanted to store it in a totally different way in here. So what I decided to do is to store that information in, again, in a no Hadoop storage, which is another one of my favorite, is Elasticsearch. Why I like Elasticsearch is because Elasticsearch has not only search capability, but also has geo search capability too. So now what I did is I took the original raw data that I have, bulk loaded it into Elasticsearch with the geospatial capability, and then use Spark to do the dynamic segmentation. So again, for the 1.7 million records that the United States, there is about 105 million highways in the United States. For the year 2013 or 2014, I don't remember, there's about 10 million events that come along with each of those segments. Again, what you have to do is you have to fuse that two information together. Typically, the traditional means takes about a couple of hours, more than a couple of hours, okay? Most like a full day to run all that aggregation, and that's hard for these guys. When I took this implementation and did it and implemented it in Spark, on my dinky Mac, literally took me 10 minutes to run that whole process. Pretty impressive on this whole thing, and generated 27 million output out of this whole thing. So when again, we brought in that old band, again back into Elasticsearch, because it's searchable, space and time. And again, using the Python mechanism, I can query this environment in here and visualize the result. Now, the cool thing is where I wanted to run it next time for the big analysis in here. So a lot of data centers spent a lot of time, guess what they're doing? They're spending a lot of time cooling their centers. So we teamed up with this company called Nerdalize, which actually pushes servers to the homes. And what do you mean by that is, they actually made up heaters of the servers. So instead of wasting time, wasting energy and being CO2 neutral here, trying to cool the servers, why don't we use the heat of the servers to heat the homes with it and put that all in a nice, secure environment in such a way that I can run any platform on it. Pretty cool job, isn't it? So these boys in the Netherlands stood up a bunch of servers up there for me, and I'm running my dynamic segmentation process on it. Again, they were very cool about it because they say, you know what, run anything you want. Here's a Docker container. So great, so I took up my Elasticsearch up there on the instance, started up my Spark jobs in there, and again, I can query it and retrieve all kind of neat things with it on heaters. Totally CO2 neutral. Pretty cool, isn't it? So when I'm running my 10-minute analysis here, you know, somebody is showering and the hot water has been generated from that. Is that cool? And again, the whole thing is you front it with a toolbox in such a way that somebody can query it. And the Spark SQL, the Elasticsearch has a SQL interface, so I can query it using good old-fashioned SQL and visualize the data on the map. And now that is pretty good, like immediately. Again, go out, retrieve the data, visualize, and expressively put it on the map. Now, the final thing that I want to talk to you guys about is something I call crazy visualization. And you've seen a little bit of it, but I really want to push the boundaries. So I've seen what the Oculus guys have done, and actually imitation is the highest form of flattery. And I started thinking about it. You know what? We're putting all these dots on a map, okay? We're throwing all these dots on a map, and it's pretty cool that we're throwing all these dots on a map, but they cannot tell us anything. What I want to do is I want to be able to aggregate by attribute and filter that attribute at different scales dynamically on the fly, okay? And so what typically we do, okay? Remember I told you we quad everything? So typically what people do is they create these pyramids. And what they do is they go out and cookie cut the world into smaller little chunks, and they store these chunks. They store the image of that chunk in the database. Actually, you've seen a little bit working. When those little things were spinning around, actually that's what was happening in here. So I said to myself, you know what? I want to do something different. I want to be able to filter out by quad a particular attribute at a particular time. And so I decided to say, why not? I have big data, who cares? I decided to go for a particular attribute, for a particular level, for a particular tile, for a particular pixel, okay? So I'm not storing the image by itself. I decided to store the pixel in the database and the aggregated value, okay? Since I have big data, who cares? I can do that. But my concern was, can I pull it? Can I pull this that fast? But storage was not a problem. And again, so in here, I used actually Cassandra to do that, and I created a table that exactly is that. For a particular level, for a particular tile, for a particular year, for a particular day, for a particular month, for a particular pixel, store me that information. You said, you're crazy, Mansour. That was the whole thing about it. Remember, it started with all crazy visualization, you know? And then, of course, created the primary index on that one. So again, I use Cassandra in here. Again, part of my no Hadoop kind of storage, what I've been seeing here. And again, I love Cassandra. It's awesome. And the Spark SQL, the Spark guys and Cassandra are really nice together. And so, you know, schemaless, key value, the ring, all these wonderful things about it. And then again, I use the Spark to take all this data and put it all in Cassandra all at once. So again, so for the geeks in the room, actually the data that I originally had was in 7Z format. So I had to write the 7Z input format, which was fairly easy to write an RDD for that, because it never existed. I really looked around for that. And LZMA did not exist. So it was very simple to write a 7Z RDD that basically now I can parse, inject, and again, if you notice down there, for all the 17 levels, emit that particular value. So group by that particular, that 0 to 17, at a tile, at a pixel, at a level, at a time, group all that information, and of course, at the end, save it all to Cassandra. Run the whole process and again, and it was pretty cool. So then, well, okay, that was fine. Stored all the data, who cares, I have big data. But can I retrieve it very quickly? And so now I coupled what we call dynamic tile render services, which is I coupled Cassandra with Jetty to be able to pull out this information and fuse it with what we call ArcGIS Online. Okay? And again, for that, we have a public API, GitHub API called based on Leaflet. I love the Leaflet API. It's pretty cool. And you can extend it with any functionality you want in here. And I was able to now, through the Leaflet API, be able to query, if you notice at line 77, I was able to query for a particular tile, for a particular level, for a particular value, dynamically pull that information from Cassandra and dynamically render it on the map in here. And so that's exactly what I want to show you here. And so I went ahead and I implemented, of course, the ye olde fashion demo. And what exactly is happening here is it's talking to Cassandra, and every one of those tiles, those pixels of those tiles are dynamically retrieved on the fly. Pretty cool. And now, because I can do that, I can filter out by the hours. So find me everything between 10 and 12 what's happening, or find me all the pickups between 10 and 12 what's happening, which is pretty cool. And you can play all these very interesting games. Find me 03 to 07 o'clock in the morning, and I'm dynamically querying that information and visualizing it, which is pretty neat. Okay? But remember what I told you, I wanted to show something a little bit different here in this experiment in here, and that is, can we do space-time cube visualization? And what do I mean by that is, can I dynamically also take that tile and on the fly create a temporal order of that version in which I can change it? So what I have now is the space-time cube that I'm talking about. Can I bring that and visualize it? And turn out from the Cassandra, from the whole Spark now and this visualization, what I call collaborative visualization, I can do this experiment in here. So what I did here is I went ahead, the final demo in here that I'm going to show you is I'm going to be able to, let me bring that information in here. Okay, so now it's retrieving the cube. It's retrieving the cube, and now it gave me now a temporal version of this whole thing, and you can see the lights. I love this light. I love these lights here, and I can change them by time, and it's dynamically going through that time and displaying that information. And of course, I can filter it and have all the analysis happening. And you can see that there's a big dip, of course, at 5 o'clock in the morning in that area for that whole hour of things happening. Pretty cool, isn't it? Okay. Come on, guys. Seriously? Really? Woo! Okay. So then I went a little bit crazier. You know, I said, what if I can take every lightning for a whole month in the United States? Okay, so I begged my people to get me all the lightning strikes. Can you believe it? Actually, that's something for electrical power, for energy, for a lot of things. Displaying that kind of information on the fly is kind of hard in here. So I took the same approach in here. I took every lightning strike for a particular month and displayed it on the map, of course, in Texas. And I can filter out for a particular month here all the data that happened on a particular day. And again, it is dynamically reflecting that whole thing. Find me all the lightning strikes between 200 and at a particular cell level between 100 and 200. You know, it will filter out, dynamically querying this whole thing in there. And again, on the same idea, bringing up the cube and doing a temporal kind of a la weather channel kind of visualization of this information. So on the 10th day of the month, this is where all the lightning strikes were happening. And I can filter out by attribute the areas where they were the most affected in here. And now you can see that's exactly what happened this is where there was a storm. I should have brought in the weather associated with that one at the time and displayed that whole thing in there. Pretty cool, isn't it? Okay, I think so. Yeah. So anyway, so big data Spark is enabling me now to have these massive aggregation, massive visualization to be able to be displayed and rendered and do some pretty cool stuff with it. So again, I think my name is Mansour. Again, I blog about a lot of that stuff at Thunderhead Explorer, and reach me at email, and I'm open for questions if you have anything. And I told you that was warp speed, and I hope you enjoyed it.
All right, we got time for a couple of questions. Who has questions? Oh, man. So energetic, you kind of, they don't know what to do. So, okay, there you go.
Hi, I was just curious why you picked Cassandra specifically for the Thunder Strike sort
right.
of.
Right. So the question was why I picked Cassandra. Actually, I could have done it with HBase or Redis or anything like that. The fact that actually why I was a little bit biased because of the Spark connector, and so that was kind of my kind of implication for that, is because I loved at the end. I loved that the fact that if you notice the gig here. The dot save as Cassandra. I did not find, there was no save as HBase or save as Redis or anything like that in my Spark pipeline. And so this is why I ended up picking this one, is because it was save as Cassandra. Actually, I did this a while back. I could have done the same thing with the save as MemSQL. It would have done exactly the same thing, just the fact that this one was done before the MemSQL guys came in. But we could have done the same thing with MemSQL, and I think we could have gotten the same experience, by the way. But that magic line was available, and that's why.
Hey, how you doing? Hey. Actually, on that same slide, the DBF7Z, that was something that you created, or that was So yeah. Could you just explain a little bit about the DBF7Z?
Yeah. I get a lot of these files. Actually, the lightning strike files that I got was all, they're huge files. And I got them all as in DBF format, and not actually in shapefile format, which is what we do a lot very well in Geospatial, but all the shapefiles were packaged in 7Z format. So I could have gone through the whole year, which I had, and unzip every file and then put it in HDFS and blah, 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 and all that stuff. But that was really painful. And I started thinking, well, you know what? What if I write an input format that does that for me directly? So I went ahead and I started looking around for the LZMA, and I could not find one. Maybe if you know of one, that'll be great. But then the one that I needed was going through the zip file and pulling out the DBF file. So then I end up writing one, a DBF7Z, that actually opens up the 7Z file, go through every item, and then takes the DBF file, makes it an RDD, and then basically streams it out as an RDD. And then now, once I have it as an RDD, khalas, I can proceed with everything else, the rest of it. So yeah, I had to write that by myself, but I'm gonna blog about this whole thing, that whole experience, and I think I'll put up that the DBF7Z as a as a showcase of what you can do with this whole thing. Of course, all of it is written in Scala, so it'll be fun. It'll be interesting actually to have that turning into into actually a data frame. That will be a much better way to do it. So if you remember, actually at the keynote, there was a DBF input, that connector. Actually, one of the things I want to do is actually turn that into a data frame rather than in an RDD, a DBF RDD, and I think that will be much better. So I need to go back, rewrite this guy, produce it as a data frame version, and I think it'll be better. So you can go to ML, you can do all kind of cool things with it. Yeah. Yeah.
Round of applause.
All right.
Mansour.
Thank you, everybody.